Hello everyone, my name is Faisal Ahmed. I am currently working with the Center of Sensor Systems as a lead stage researcher and a PhD student at University of Siegen, Germany. I would like to thank the conference organizers for providing me an opportunity to present our work titled Pseudo-Passive Indoor Time Applied Sensing, Exploiting Visible Light Communication Sources. My co-authors are Miguel, Heredia, Conde, and Otmar Loffeld. They are also from University of Siegen, Germany. So let's start the presentation. My presentation outline is divided into the following sections. I start with the introduction with the proceeding sections. Later on, I will give some insights how we achieve passive sensing modality. After that, I will show simulation results and finally conclude my presentation. So let's begin. So in existing time of flight system, one of the challenging problems is a dedicated illumination unit that it consumes high power and it may raise safety concerns in specific scenarios. In last few years, the rapid progress of semiconductor technology that has changed the lighting infrastructure from lamps to the LED lights, as you can see on the right side, the image of LEDs. Nowadays, intelligent illumination infrastructure provides multiple services like illumination and communication simultaneously. On the right side of the figure B, you can see that the LED provides the illumination and it also provides the communication services in indoor lighting infrastructure. So this results the ubiquitous presence of modulated light infrastructure. This is the motivation behind this work, to use the available modulated light signals for 3D passive time of flight imaging. So one of the well-known method of communication is a visible light communication, which is available in indoor environments. Visible light communication is a high-speed communication wireless technology, which uses visible light spectrum. As you can see from the figure, that visible light spectrum is much more than the radio spectrum, and it provides the high-speed communication services. And the VLC infrastructure providing the same level of lighting at low cost with the additional service of communication. So VLC is one of the well-suited technology for indoor environments because LEDs are widely used for illumination and now they are used for the communication. And this means the LED, the light becomes a data. So indoor light sources or lamps are rapidly replaced by the LEDs, and in turn, the LED sources becoming internet access points. And this paves the way to an emerging data communication known as a VLC. As you can see on the right side of the figure, that data signal is transmitted towards the driver circuit, and drivers modulates light towards the LED lamp. LED lamp transmits the light signal towards the photodiode, and photodiode converts the light signal to the electrical signal and amplify it and process it to get retrieve the transmitted data on the receiver side. So this is basically the indoor visible light communication link that provides both simultaneously lighting and communication. So let's talk about the time of flight imaging. Time of flight cameras are active sensors. They are able to measure the depth between the sensor and the scene points, and they are generally illuminated by the active illumination unit with the amplitude modulated IR light for suppose 850 and 940 nanometers of range. ToF sensors are ToF sensor operation are broadly classified into two. Based on the modulation waveform nature. For suppose continuous wave, in continuous wave signal is used for the illumination, and for the demodulation control signal, the sinusoidal is not exactly used for that, but we are using close to the square signal or trapezoid signal for the synchronization. And in pulse time of flight systems, the square signal is used for the illumination, and the same signal is used for the demodulation. As you can see in this figure, the signal is transmitted towards the object and reflect back. So based on our ToF operation, if we are using continuous wave, by finding the phase difference, we will get the depth value. If we are using the pulse time of flight, but finding the time difference between the emitted and reflected signal, we would get the depth value using the above formula, which is represented in the figure. One of the well-known technology for the time of flight imaging is a PMD, photonic mixer devices. The underlying principle of PMD pixel uses the shifted version of single demodulation control signal to enable the uniform samples of autocorrelation function between the reflected signal and the demodulation control signal. So here EQSpace samples of autocorrelation functions are used to get the measurements and add 4 phases for suppose A1 to A4. And using the 4 phases algorithm, we will get the phase offset, phase shift, and this phase shift gives us the depth value. So now we will talk about the passive ToF sensing model. So we take the profit of existing modulated light signals, and for the first time, we are using the VLC as an innovative idea to use this concept for the passive 3D time of flight sensing. And in this scenario, the time of flight camera and the illumination source are synchronous, and the signal is transmitted towards the object that illuminates the scene, and the reflected signal is acquired by the PMD sensor. In this scenario, we are using sinusoidal signal for the synchronization purpose to get the depth value. So the OpenVLC module is used for this purpose, and that supports Manchester encoding on off-key modulation. And this module contains a single LED as a light source that's used for the communication and also for the illumination purpose. Let's suppose an optical theoretical signal is modeled by the following equation. And this equation T represents the time period, and QM simply translates pair of bits of ones and zeros. The binary bits for suppose 0 and 1 are high during the first and second sample period, respectively, and otherwise low. This is the property of a Manchester encoding technique. So this translates this 1 bit into 2 levels. However, the probing function does not exactly coincide with the theoretical optical signal because the low pass effects of LEDs, and this is obtained by performing the convolution between the threshold of theoretical optical signal with the LED impulse response to get the probing function. And further, probing function is convolved with the scene response function that define the weighted sum of direct delta functions, and model is HT PP factor represents the time shifts. The corresponding reflected signal is follows. For suppose this is convolved with the scene response function and the probing function that provides the reflected signal. As a demodulation control signal, we use sinusoidal signals at the dominant frequencies, and this is represented by this equation. In this equation, F represents the modulation frequency, and Q 5K is the Cath phase shift, and can be written as 5K term is represented by this term, and for K belongs to 1 to N is the number of samples of autocorrelation function. So we obtained for obtaining the measurements at both dominant frequency, this model can be used. And in this model, Rn is the reflected discrete time domain signal, and Mk is the discretized DCS signal. In time of flight, in PMD cameras, n equal to 4 samples of autocorrelation are used to obtain the phase and amplitude of that scene responses. So in PMD sensors, we are using 4 samples, that means 4 phases and 4 measurements. And after using that four measurements, we will use one of the well-known standard tool for phase retrieval in continuous time of flight system. That is a 4 phases algorithm, is outlined in our in previous slides from equation 1 to 4. So we coming towards the simulation results and the real optical signal on the in figure number 8. This is the real optical signal acquired by the ToF photodiode and transmitted from the OpenVLC module. On the right side is the autocorrelation function, and below figures that shows the RC model low pass model signal and its autocorrelation function. And this, as you can see from these figures, that the similar pattern from the model signal responses mimics the similar behavior in the real optical signal. So the RC values are acquired from the real optical signal to get to model this response. And in this figure, this is the frequency spectrum of a VLC optical signal that provides 2 dominant frequencies. And these dominant frequencies are used for the demodulation control signals. On the right side, you can see the Manchester coded signal. And this is the basic theoretical optical signal, we can say, theoretical optical signal. And this represents 2 levels for each bit, and this and goes on. In these figures, we obtain the estimated depth based on 2 ranges. First is the 10 meters range, and other one is the 45 meters range. For both the cases. In first case, for the 10 meters range, we used two dominant frequencies for the demodulation control signal to obtain the estimated depth, and the depth error below 0.6 millimeters range. And for the other case, for 45 meters range, we find out the depth, estimated depth below 14 millimeters and 0.2 millimeters range for F1 and F2 frequencies. As you can see, there is a unknown depth offset is observed. This is due to the mismatch of frequencies, and also it's because of the asynchronous between the illumination source and the sensor. So let's finally conclude the talk. Eliminating the need of illumination unit and the optical filter from existing ToF sensors, and making use of opportunity illuminators, for example, VLC sources for passive 3D imaging. And VLC infrastructure can support synergistically multifunctional features like lighting, communication, 3D imaging. Our simulation results shows accurate depth estimation on is attainable both in short and long ranges. Our approach opens new directions and questions in context of application scenarios where VLC infrastructure and the ToF sensors are valuable assets. So this is all about our work, and these are the references. And thank you for your listening, and thank you for EU funding this project. I am happy to answer your questions. Thank you.